Hey there, chemistry students. This is Ms. Ruark. This is vodcast 9.3. We're going to talk about acid-base stoichiometry. Now, as I've already mentioned in class, you've already seen this before. We called this solution stoichiometry. It's still the same thing. I just wanted to touch base on it again and do some more practice with you in case you needed that extra practice before we get to our titrations, because our titrations are all stoichiometry. Okay, so this is all about examples. So example number 1 says zinc reacts with 100 milliliters of a 6.00 molar cold aqueous sulfuric acid, that's a solution, through single replacement. Okay, this is giving you all the information you need in order to write the reaction. So we know in this reaction we have zinc reacting with sulfuric acid, H2SO4. Right? Anytime we do any type of equation or math, we have to have a balanced chemical equation. So we're writing that. We know that this is a single replacement reaction, which means one thing trades places. Zinc has a positive charge, so it replaces the positive charge. So on the other side, we have ZnSO4 plus H2. Nothing new here. You've seen this before. Okay, so let's balance it. We have one Zn, two H's, two H's, one SO4, one SO4. It's already balanced. Love it when that happens. Okay, so the first question says, how many grams of zinc sulfate are going to be produced? So we want to know how many grams of ZnSO4 will we make if we start with 100 milliliters, 100 milliliters of a 6.00 molar H2SO4 solution. Okay, remember, whenever in doubt, I don't know what I'm doing, go to moles, okay? Can I start with anything on the zinc sulfate side? No, I don't have any numbers for it, but I do have these numbers. Can I use these numbers to go to moles? Yeah. How do we know? Molarity is equal to moles per liter. All right, so let's take this and plug it in for molarity. Let's plug this in for, oops, we can't plug in milliliters for liters, but we can change milliliters to liters and plug it in, right? Okay, so we remember that 100 milliliters, point. All right, and to change from milliliters to liters, we know that 1,000 milliliters is equal to 1 liter. So we're going to move that decimal over 1, 2, 3 times. That gives us a 0.100 liters. Don't forget those zeros because they are significant, right? Yes. Okay. So let's plug all that into our equation. So in our molarity equation, we put in 6.00 m is equal to X. That's what we're looking for. No, we're not, Ms. Ruark. We're looking for grams. Right. But we can go from moles of one thing to moles of another thing to grams. Oh, yeah, that's right. Okay. All right. And then for liters, we plug in 0.100 liters. All right. Now, to get rid of this, I have to multiply both sides by. All right. Nothing new here. 0.100 liters. What I do to one side, I have to do to the other side. So 1.00 liters. Those cancel. X, remember, that's moles. Okay. So 0.1 times 0.6 or 0.1 times 6, sorry. Okay, so X, which is moles, is going to give us 0.600 moles of H2SO4. But that's not what we want. We want grams of zinc sulfate. Well, now it's just a regular stoichiometry problem, right? We can go from H2SO4 to ZnSO4 by using our mole ratio. And we say there's moles of H2SO4, so moles of H2SO4 goes on bottom. Zinc, moles of ZnSO4 is what we're looking for, so we're going to put that on top. And it's a 1-to-1 ratio, so we fill in our moles. Okay, but we're not done. We don't want moles, we want grams. So let's keep going. We know that 1 mole of zinc sulfate is equal to the formula mass of zinc sulfate. Now, I've already done the math for you. It's 161.46, but hey, I'm sorry I jumped the gun on that one. If you want to next time, pause it, and then you can do the math on your own and check your answer. Okay, so now moles of zinc sulfate cancel, and we're left with grams of zinc sulfate. And look, that's what we want. Oh, yeah. Okay, so now all we have to do is the math. So 0.600 times 1 divided by 1 times 161.46. Go ahead and plug it into your calculator. I'm getting ready to give you the answers, so if you want to check your math, go ahead and pause it. All right, so the calculator gives us 96.876 grams of ZnSO4, but guess what? We need to check significant figures. Oh yeah. So we go back to the original numbers from the problem. There's 3 here, there's 3 here. We need 3 significant figures in our answer. So we make this a 96.9 grams of zinc sulfate will be made. And that is our answer. Oh yeah, lots of fun. All right, so the next question says, well, how many liters of hydrogen gas would be released at STP? Okay, so we're pulling in stuff from gas laws, you dirty little devil, Mr. Ark. I know, it all builds. All right, so at STP, we know that 1 mole of any gas is equal to 22.4 liters of that gas. It's going to make it so easy. So we take those moles. Let's not do any extra work that we don't have to do. So we know that we have this many moles. So we're going to use those moles because I don't want to do the extra work. Do you? I hope not. If you do, go for it. All right, so we know this many moles of H2SO4 is going to react, and we need to go to H2 this time. So we set up our mole ratio, 1 mole of H2SO4 to 1 mole of H2, because that's what we're looking for, right? We're going to hydrogen gas. Right? And then we just set up our next one. We know that 1 mole of hydrogen gas is equal to 22.4 liters of hydrogen gas. This is all just review. That's why I'm going quick. All right, so 6, this cancels here, this cancels here. So 0.6 times 1 divided by 1 times 22.4 gives us, calculator says, 13.44 liters of H2. But we got to go back and we need 3 significant figures again. So 13.4 liters of H2, and that would be your answer. Oh yeah. Okay, so the next 2, we're going to go through them. If you think you've got it, go ahead and try it. Come back and check your answers. And if not, then just stick with me. All right. A volume of 18.28 milliliters of a standard 0.1000 molar NaOH solution was used to neutralize. All right, so we know that we're reacting NaOH to neutralize an acid, methanoic acid, which is HCOOH. And they say, what is the molarity of a methanoic acid? All right, so these 2 reacting are going to end up producing H2O and then NaCOOH. How did I know that? Remember, the H comes off and attaches itself to the OH. Everything else left over goes together. All right, is it balanced? You betcha. It's the beautiful thing about most of these acid bases are going to be balanced already. Most of them, not all. All right, so we know that we've got 18.28 milliliters of this sodium hydroxide, and the concentration is 0.10000 molarity. And we used 25 milliliters of this solution, but we don't know what the concentration is. That's what we're trying to find. Okay, so we can't start here because we don't have anything else, but we can start here and go to moles, can't we? We sure can. All right, so we've got to set up molarity is equal to moles per liter. We plug in 0.1000 molarity is equal to X. That's what we're looking for because we're looking for moles. Okay, and then don't forget this needs to change into liters, so 0.01828 liters. Okay, multiply both sides. I'm not going to do the math because you already know how to do it, but X here is going to be equal to, oh, maybe I should do the math because I don't have it already answered. All right, that gives us 0.001828 moles of NaOH, but we don't want moles of NaOH. We want to get to this thing. So to go from one thing to another, we use our mole ratio. All right, we know that 1 mole of NaOH here can react with 1 mole of the HCOOH, which means that we have 0.001828 moles of NaOH. But guess what? We don't want moles, do we? We want molarity. And we know that molarity is equal to moles over liters. Well, look, we have moles of NaOH. Or, no, sorry. HCOOH. Right? I didn't cancel those, that's why. All right, so we know we have moles of HCOOH, and we have milliliters, which we can change into liters. So can I use that to figure out my molarity? I sure can. Moles over liters, right? Oh yeah. All right, so we've got those two, and we just solve for molarity, which gives us 0.07312 moles per liter, which is the same thing as molarity. And then we look up here and we say four significant figures, four significant figures, four significant figures. Looks like 4 is the magic number, and there's our four significant figures. Boom, there you go. It's not that hard once you start doing it. I promise. We'll do some more practice in class. Don't worry. Don't freak out. Okay, let's go on to the next one. Here's our last one to do for the vodcast. So it says, example 3, if 28.55 milliliters of a 0.1200 molar LiOH is used to neutralize, oh, looky there, here we go. LiOH is used to neutralize perchloric acid. You guys' fave, PHClO4. What is the molarity of the perchloric acid? All right, so we're going to produce on the other side water and lithium perchlorate. Okay, simple double replacement reaction. Okay, then we double check to see if it's balanced, and guess what, guys? Yeah, it's balanced, so we don't have to worry about that. All right, so we've got 28.55 milliliters, and it is a 0.1200 molarity. And we're using 25.00 milliliters of perchloric acid. They want to know what is the concentration of the perchloric acid. Same stuff. Whenever in doubt, go to moles, right? So molarity is equal to moles per liter. We solve, or we plug in 0.1200 m is equal to X over 0.02855 liters, because I changed that from milliliters to liters. Okay. All right, so there we take 0.1200 times 0.02855, and we end up with X, which is moles, is equal to 0.003426 moles of lithium hydroxide. But we don't want moles of lithium hydroxide, we want moles of perchloric acid. So we use our mole ratio. It's a 1-to-1 ratio, which means that we have 0.003426 moles of perchloric acid. All right, well, guess what? We want molarity. And remember that molarity is the same thing as moles over liters. I have moles of perchloric acid. I have milliliters, which means I have liters. 0.02500 liters. And so now I just have to plug that in and solve for it. And I get 0.13704. Right? We look here, I've got four significant figures, four significant figures, four significant figures, so I want four significant figures. The 4 does not make the 0 change at all, so it's 0.1370 molarity HClO4. And that's all you have to do. So this solution stoichiometry or acid-base stoichiometry is just kind of pulling it all together and saying, hey, let's have some fun with this. All right, when you guys get to class, we're going to do lots of practice. I've got 5 practice problems for you in your packet. I'm going to have some more practice problems for you to do in class as well. All right, and if you have any questions, let me know, and I will see you then. Bye.